Our next speaker is Dr. Casey Durande's physics student, Ms. Alyssa Krehbiel. She will be presenting on electric thoughts.
All right, everyone. Thank you guys for being here today. My name is Alyssa Krehbiel, and I will be presenting my project, Electric Thoughts. And I'm going to warn you right now, I'm going to be talking a little quick because there's a lot of ground we got to cover, so let's get to it. So this project I did on is about electrical physics being applied to electricity inside your brain. Now, what we're going to be going over is the basic workings of the brain, nervous system, and neurons, as well as electrical physics applied to these systems and some of the applications that we can use them for. Now, the brain is probably the most fascinating and complicated and elusive electromagnetic and biological system that's ever been created. It's something that we're still figuring out today with all the technology that we already have. And so, that study of what we're trying to figure out is called neuroscience. Now, neuroscience, even though we've been interested in it since the dawn of time, it's only really taken off in the last century or so, due to the fact that we now have the EEG, the PET scan, the MRI, and the fMRI, which allows us to actually look at the electricity inside of our brain. We're trying to bridge that gap between psychology, where it's abstract thoughts and behavior, how you can see something inside your mind, and the electrical impulses that's going around in this gray matter that's just inside of our skulls. So the nervous system is split into two parts, the CNS and the PNS. And I'm going to be going over the CNS, the central nervous system, even though they're all a part of the same system. And the brain is the central hub for both of them. It's over 1 billion nerve cells and determines what we all feel, see, and experience. And so the basic building blocks of this system are neurons and glial cells. And we're going to be going over neurons, although glial cells are fascinating in their own right, but we don't got time for that. And so neurons themselves are kind of the electrical circuit at the smallest form inside of our body. So there are different types of neurons. There's motor neurons, and then sensory neurons, and then also involuntary actions. So, for example, if I were to stub my toe, the neuron at the bottom of it would tell me that I'm in pain, go all the way up to my head, and then I go, oh my gosh, what the heck, that hurt, and then I get angry, and then I use my motor neurons to kick the thing, because, you know, we're humans, we're not technically logical, but that's how we use our neurons. And then in involuntary moments, that does glands, and then your heart, and how you can breathe, because I don't know about you, but I'm not actively thinking about my heartbeat. And so then the communication between these neurons works through the structure of the neuron. So we have the electrical signal that's sent down the axon, which is kind of like that long piece right there. It sends down an electrical signal down to the terminals, which create a neurotransmitter, or a chemical messenger that goes through the synapse to the next neuron and receives it at the dendrites, which then return it back to electrical energy. So basically, we have a repeating process of chemical to electrical energy going on back and forth. So we as humans are fantastic conductors. We can conduct electricity very well due to the fact that we're mostly water, as well as different lipids, liquids, and salts, which makes us great for conducting electricity through our neurons, also too scared to go swimming during a thunderstorm. And so cells and neurons, we have cells, neurons, and ions. We have different ions in our system at any given time. The most important ones I'm going to be talking about today are going to be the sodium and potassium neurons, or K+ and Na+. And so the charge of a cell, whether it's negative or positive, depends on the ions and the permeability of that cell membrane. And in the case of an axon, we're going to be using that membrane to go over the potential difference and how that creates an electrical charge. So at rest, the charge of an axon is negative, and that's due to the fact that the permeability of that membrane is letting out more positive than it's letting in positive. So more or less, we're going to have a negative inside and a positive outside. And that membrane potential is going to become very important when we get into the very big physics side of things. And that's going to be represented by, actually, that V is not velocity for anyone who might have thought that. It is voltage, just in case. So it's going to be our voltage of the membrane times the time. And then we also have the dendrites, which I'm going to touch on right now. And so dendrites actually are the ones that receive the neurotransmitters. They have specific proteins that let in those neurotransmitters and then convert them into electrical energy. And those electrical impulses that are being transformed, that's going to be our action potentials. And this is something I'm just going to touch on very lightly and come back at the very end, but I wanted to get it through now. Brainwaves are kind of where everything is going towards, and this is where we actually have to further our research as a neuroscientific community. So, brainwaves are the oscillations of billions of neurons working in tandem. This is what we can observe. This is the alpha waves, beta waves, things that you hear about when you think about sleep, but you don't actually know what they mean yet. That's your brain functioning at a certain frequency. And these frequencies actually depend on, or they predict, that's something that's still kind of a question, what kind of thoughts you're having, how awake you are, how active they are, and whether or not you're in deep sleep, of course. But we will get back to that, because we're going back down to our neuron level. And this is where our physics can come in, because as cool as it'd be to stand here and talk about biology, this is physics. So physics in the brain, we're going to start off with our neurons. So define some variables real quick. I know this is very text heavy, so I'll try not to go too long. So we have our neuron N, which is going to be our presynaptic neuron, and our neuron M, which is going to be our postsynaptic or resting neuron. So the membrane potential, as I went through last time, is going to be our voltage of M times T. So if you're at rest, then it's going to be our V rest, and that's going to be a very important one. So whenever the time is above 0, so when it's not at rest, then you can find that using the calculation. All right, so we have our calculation of the voltage time, which is going to be the M times the time that's above 0, minus the V rest, so our already established variable, and that's how you can get to the voltage M and T. And now something that's important to remember is that the interconnection of neurons is not linear. If you've ever seen kind of a map of what your brain looks like with neurons, or even just like an artistic depiction, it is many neurons to a single neuron. It is connections going between one another. They don't just connect in a single line. That's not how that works, especially inside of the brain. And then another model that we can look at to try to boil down a neuron to more of an electrical perspective is the three-state excitable model. So we're going to put values basically to the 3 different states that a neuron can be in. We have the activated, the resting, and of course the refractory period, which are all denoted by 0, +1, and -1. And more or less what this means is the value of the system should be equal to whatever point it is at. And the important one to look at here is that one down there that has the there we go, the activated to refractory, it has to actually be larger than this threshold that causes it to go into a refractory period. And how long it stays in that refractory period, and basically how long that life cycle is, can be found by using a basic physics where it goes T the average equals -1 over the log of 1 minus PG, and the PG is our transitional probability. And this is where things get a little more complicated trying to look at something from a basic mathematical point of view, because the transitional probability varies from neuron to neuron. And so you can see, if you look at a graph here, the transitional probability is basically how likely is it to transition, how easy is it to get that to move along. And the more you don't use neurons, the more that goes down. So keep up your memory. Finally, you have the leaky, integrate, and fire model, which is probably the most electrical way to look at a neuron because you can model it as a circuit. So this actually makes me think of one of the earlier presentations where we were talking about batteries. That's essentially what we're looking at right now. So you can model cells into a parallel circuit, and then what happens is you can change the capacitance of the circuit to the membrane capacitance, and the same with the resistor value. And so you combine them into a series with the battery EMF that's equal to the V rest, the voltage rest that we went over earlier. So the capacitor's current you can find using the Q equals CV principle that is used in almost all electrical physics. And then you can find that current using the derivative right there. And then this is where some realism comes into this model, is the leaky resistor. So as I said earlier, there's a permeability to all of the cells. There are positives and negatives coming out. The ions do drift through occasionally. And so this leaky resistor can be seen right there where you find the current of the resistor. And then using Kirchhoff's law, you can find the total current of this system, because all currents summed together is going to be equal to that. And from there, you can find your time constant using the resistor times capacitor, there we go, sorry, a little dehydrated. and from there you can derive it further and further. And honestly, there's a lot more to this, but for the sake of time, I had to cut it down. So I just spat like a lot of physics at you and some basic biology, but the question is, what's the point of this? Why does this matter? Of course, we all have electricity in our brain. We're basically large bags of water with electricity shooting through us at any time. But here's the thing, is that the future research and the questions that we still have unanswered, they can lead to some interesting things in society. So one of the research things that have happened recently is MIT has discovered that actually the whole chicken egg problem that it comes to the brainwaves might be solved. So the hypothesis is that, oh, that is not in frame, oh, that's sad. So the hypothesis is that active thought is predicted and dictated by the type of brainwaves that you have. So the question is, do your thoughts dictate the brainwaves? Do your brainwaves dictate the thoughts, or are they the same thing? That's where all the questions come in. And then also something that's an interesting application is treatments for Parkinson's disease. Now Parkinson's is actually, there's the thalamic cells that oscillate at a low frequency. Basically they're oscillating half asleep, so they can't connect to their motor neurons. That's why the failure of movement is such a problem. So one of the things that someone's proposed recently is that a pacemaker to correct the oscillations could at least improve the quality of life, if not maybe solve Parkinson's, but it's still all in theory. And some questions that we still don't have answered, which I think is what neuroscience is going towards right now, really has to do with brainwaves. Because as a whole, the question is, how does electricity transition into what we're doing right now? You can see me right now. You're having abstract thoughts. You can think about things you're going to do in the future. You can visualize a book. You have abstract thoughts about humanity, life, philosophy. How does that come from some electrical impulses going through gray matter? Brainwaves, I think, might be the answer. But the problem is that we are still trying to understand them. We can't observe the life cycle of a single neuron in a brainwave yet. We're getting there. But that's going to be in the future for still. So in conclusion, I think that this can actually benefit society as a whole if we continue with neuroscience, not only help understand us, why we're here, what are we doing, what's life in general, but also help quality of life for people who have mental disorders and problems that originate from the brain. Any questions?
I apologize, I'm not sure if you mentioned this, like I missed it, but are they bringing technological, like the computers who are trying to build neural networks, can you tie that into this research, going from understanding single neurons to understanding like the brainwave overall?
Oh, absolutely. That's actually something that's really helped with understanding of the electricity inside the brain in general, is that the fact we're building computers with brains and trying to, if you said build an AI, you have to find a way to get abstract thought from computer circuits, so that's going to be a question that everyone has to answer there. Yes?
I know you went mostly with the central nervous system, but is there any research going into prosthetic limbs and having some sort of synthetic meeting with biological neurons?
That was a little outside the scope of my research, but I actually have read a couple things on that there's research that's currently being done to try to figure out how to do prosthetic limbs that can respond to neurons and neural networks. It's still very much in the rudimentary works, but it is a current topic going on. It's very interesting. Anything else? All right, well, thank you for your time.